Let's go ahead and get started now. So what are we doing today? We are going to be able to solve optimization problems and find the most or least possible quantity. How are we going to do this? We're going to build a function for our quantity. We're going to take the derivative and we're going to set it equal to 0. Sounds like what we've been doing for the past couple weeks, right? And so, like, we've been talking now for this whole last week about maxima and minima and how to figure out when you find the top of the hill or the bottom of the valley or the endpoints, if those are the max. This is basically now we're going to take this, we're going to apply it to like actual situations. So basically, what we're doing today is going to be fancy dressed up problems. And I will tell you in advance what the hardest part of doing this is. The hardest part about doing this is creating the equation or equations plural that you're going to be working with, because it's like you're going to get the information, you're going to have to build the equation yourself, and you're going to have to figure out what you're actually looking for. So I've pulled together some examples, um and I want you to remember, like, there's no one right answer necessarily, but it really does boil down to what did you come up with? How did you come up with it? And what are you doing with it? And as long as you're doing good math with everything, you should get the right answer. Um, so let's begin. So here they're telling us to find the smallest perimeter and the dimensions for the rectangle that has an area of 196 inches squared. So first things first, smallest, and then what do we want the smallest to be? The perimeter. So our function that we're going to minimize is the perimeter function. So I like visuals. I'm a very visual person. Here's a rectangle. I'm going to be like, all right, we'll call one of these X and one of these Y. You can use whatever letters you want. It does not matter, right? So perimeter and area are what they talk about. So perimeter and area are what we're going to use. What's the perimeter? X plus Y plus X plus Y, right? What's our area? It's 196. But what is it in terms of X and Y? So one of the things that you're noticing, I hope, perimeter, this is what we're minimizing. Area, they actually gave us a quantity to work towards. So I really like to compare this section to the related rate section, because what you're going to be doing today is you're going to be creating all these little special bespoke equations for this particular individual situation. We're going to steal from sort of the generic things that we know. What's the generic perimeter? 2 length plus 2 width. What's our area formula for rectangle? Length times width, right? Well, we don't have any information about like the rates at which things are changing, and that's fine. We don't need them. But what we do know is that either way, we're not going to be able to do this with these two variables here, because we don't have the rates involved. So we want one variable so we can take the derivative with respect to the one variable. And it doesn't really matter which one we choose. I tend to go with X just because, but it doesn't matter. It really doesn't matter. You'll get the same answer whether you solve for X or you solve for Y. So what I'm going to do is I'm going to take this area and I'm going to solve for Y. So I can have everything in this perimeter in terms of X, so I can take the derivative with respect to X. So Here, I'm going to divide the x over, right? So now I'm going to take this and I'm going to put this into the perimeter formula. 2x plus 2 times y. Well, what's y? Right? Well, let me multiply this. So we got, was that like 392 over x? Sure. So now what I'm going to do is I'm going to take the derivative with respect to x, and I'm going to set it equal to 0 because I want a minimum, right? I want the smallest perimeter. Derivative of 2x is just 2. The derivative of 392 over x is negative 392 over x squared. And I'm just going to solve for x. So I'm going to solve for x over here. I'm going to basically take the negative 392 over x squared and move it over to the other side. Right? And then I'm going to sort of, you can cross multiply or whatever, however you prefer to think about it, but you end up with 2x squared equals 392. And now we're just going to solve for x. Now, since we're dealing with dimensions, we're dealing with geometry, we're dealing with lengths, those are always going to be positive numbers. So when we take the square root here, you know that you're not going to need to worry about the negative. So 196. And the square root of 196 is 14, if I remember correctly. 14 times 14. 196. Good. Yeah. So here we got x equals 14. So that's x, right? Well, if x is 14, what's y got to be to make an area of 196? 14 times what is 196? 14, isn't it? So the smallest perimeter, well, we got to know what the smallest perimeter is, right? Because that's what they're actually asking for. So we found x and y. X equals 14, y equals 14. So we're going to do 14 plus 14 plus 14 plus 14, which should be 56 inches. That is our minimum perimeter. Right? So let's go over what we just did, just so that we're all clear. Thing I did first is I wrote down my information. Thing I did second is in the function I'm going to minimize, I made sure that there was one variable. I did this by solving for the other one with the other equation. Once I plugged that in, I simplified it, took the derivative with respect to the variable, and solved for the variable here. Once I did that, I put it back into the context of the original problem, found all the player pieces, and then once I found all the pieces, I went back to the original directions and looked for the thing that I actually needed to answer the question to. In this case, it's the smallest perimeter. And what is that? Well, if all these are 14, 14, 14, 14, 14, I get 56. Okay? So that's what we're talking about here. So they give a picture, which is really nice. I would honestly probably draw the picture myself if they hadn't given it to us. Let's make it bigger so it's easier to see. There we go. So you'll notice we got 3 parts here. We want to find, and actually what's really nice is that they're basically talking us through this problem. But like, okay, express the y coordinate of P in terms of x. Well, we know the x coordinate we're calling x. They're trying to hint to you that that's going to be what we're going to like take the derivative with respect to. So let's start with what's the actual equation of this line here, AB, right? Because if I know the x coordinate is x, I can find the y coordinate by just, well, what's the y equals, right? So they give us a point right here, the point 11, 0, right? And we need the slope. So we need to know what this is. What do they tell us? They tell us that this is an isosceles right triangle, yeah? Well, if this is an isosceles right triangle, then we know that this height here is the same thing as this distance here, right? You know, you could go through and you could be like, all right, well, this whole thing is 22, so this is this this side piece is 22 radical 2, or 22 divided by radical 2. And then you could do it again because this is also a 45, 45, 90 triangle in here, which means that this is 22 divided by radical 2 divided by radical 2, which is 11. But like, you know, if you've got an isosceles right triangle that's a 45, 45, 90 triangle, this piece is also the same as this piece because it's another 45, 45, 90. So up here, this is also 11. That's a really long way of saying, hey, this thing's 11. It's the same as this. You can take that to the bank. It's always going to be exactly the same. So look, what we have here, we've got goes from 11 on the y-axis down to 11 on the x-axis. You know, you can really quickly find that the slope here is -1. So now I'm going to go through. I'm going to use my y minus y1 equals m times x minus x1. What am I doing? X1, 11. And then distribute and then solve. Y equals -x plus 11 is our function. We are expressing the y coordinate of P in terms of x. So y is -x plus 11. So what can we do with that? Well, so first of all, that's part A. Express the area of the rectangle in terms of x. Well, so first thing we should probably do is recognize that this rectangle is centered here. So that means that whatever this piece is, so is this piece, right? So if this is x, this is x. And so the entire length is 2x. And then what's the height? Is y. So for part B, I would always begin with multiple variables. The area is length times width, so we know it's 2x times y. And then they say in terms of x, that means, hey, we need to get y in terms of x. Well, we did that already. That's what we did in this first part. So let's rewrite it. Let's rewrite y in terms of x. 2x times what? Y, which is -x plus 11. Now, here's what I'm going to tell you. When you're going through this and you're going to actually do stuff with this, you're going to distribute this. because this is easier to take the derivative of than this. I hope everybody remembers that. I mean, I'm not going to yuck your yum in here. If you would rather take the derivative of 2x times the quantity negative x plus 11, you go right for it. I got you. Do that, but like, this is much easier to me. So now, I want to know what's the largest area the rectangle can have. Largest. Key word there. We are optimizing. We are finding the maximum. Area. Well, isn't this the function for area in terms of x? So look, I'm going to take the derivative and set it equal to 0. The derivative of negative 2x squared, that's negative 4x. The derivative of 22x, that's just 22. And then I'm going to solve for x. I'm going to add the 4x over to the other side. I'm going to divide both sides by 4. You can simplify this down to 11 over 2 or 5.5. I don't care what. Whatever helps you. And if x is 5.5, what's y going to be? Negative x plus 11, which is also 5.5. I'm not going to say that there's a pattern here sometimes, but there's totally a pattern here sometimes. So here we've got our x and our y. Let's go back up. Our area is 2 x, y. Well, what's x and what's y? Right? I want to say it's like 61.5. So if I did 11 times 11, that's 121. And I just divide it by 2. Yeah. But like, I'm not, use a calculator if this is annoying. But 61.5 would be the largest area. And that's in, do they tell us? They tell us units. The area is 61.5 units squared. And then they want to know the dimensions of the rectangle. Well, we know what x is, we know what y is, and we also know what the dimensions of the rectangle are. The length is 2x. The width is y. So let's plug those in. The length is 5.5 times 2. The width is just y, 5.5. So once again, I want to point out the similarity between the last problem and this problem, not just in terms of the fact that, hey, there's a rectangle, but also because we did the exact same thing again. We found an equation for what we're trying to maximize or minimize. That was number one. Number two, we found a way to make sure that there's only one variable in the problem, usually by finding some relationship between our two variables so that we can make just one variable for our time right now. Then we took the derivative, we set it equal to 0, and we solved, and then we plugged everything back in where it needed to go. Every single problem, this is exactly what you're going to do. You're going to get the function you're going to minimize, make sure that you can get all the variables in terms of one variable so that you can take the derivative properly, take the derivative, set it equal to 0, solve for the variable, put it back into context. If you can do that, you can do every single problem in here. Here's another rectangle. Now they're trying to make things complicated. But it's the same idea. It's the same idea. They're telling you that there's a rectangle with a base on the x-axis, so just like this one. The only difference is that it's no longer this isosceles triangle, but it's a parabola. And the two corners here are on the parabola, like this. So I'm going to attempt to draw this because I think a visual is a good thing. Let's see what I can do. Um, gonna say that better not be. Here's my axes. I'm gonna cheat down a little bit because I know that everything's gonna be up here. And then I'm gonna try and draw a parabola. So I'm gonna cheat and I'm gonna draw the rectangle first. I'm gonna try and make it centered as I can because it's centered just like the previous one. And then I'm gonna attempt a parabola. Wish me luck. I teach geometry so I can avoid drawing parabolas. Hey, I have done so much worse before. And they tell you that the equation is 100 minus x squared. So we know if we were to solve for the zeros of this, x squared equals 100, x equals 10, and negative 10. And at 0, we have 100. But somewhere on here, we've got at the point x comma y and the point negative x comma y, right? These two spots where this rectangle is hitting the parabola. So we want to know what are the dimensions of the rectangle that have the maximum area, and we want to know what's the area. So the exact same thing. The only difference between this problem and the previous one is that the previous one's not going to hold our hands through it. But on the other hand, they have given us a choice piece of information right here that y equals 100 minus x squared. Well, let's get our equation for area. This piece has a length of x, that piece has a length of x, and this piece has a length of y, right? So what's the area gonna be? Well, x and x is 2x. That's our length. Y is our height. You'll notice it's just like the previous one. But now, instead of y equaling what we made it to equal before, it's going to be 100 minus x squared. That's our... Now we have our function only in terms of x. And once again, like before, I am going to distribute because I don't want to have to do multiplication rule. Or chain rule for that matter. So I got 200x minus 2x cubed. And now I'm going to solve for the derivative equal to 0. So let's take the derivative. 200x, the derivative is 200. Bring down this 3, you got 6x squared. Now I'm just going to solve for x. Divide both sides by 6. We get x squared equals 100 over 3. So 10 over radical 3. That's what x equals. 10 over radical 3. Well, if that's x, what's y? Well, let's find out. 10 over radical 3 squared is 100 over 3, right? And then so 100 minus 100 over 3, so this is really 300 over 3 minus 100 over 3, which is 200 over 3, right? So I got my x, got my y, that's my dimensions. Now I'm going to find the area. Remember, our area is 2xy. 2 times 100 over 3 times 200 over 3, right? Radical 3 here, right? Let me double check everything. Yeah, 10 over radical 3. Just going to take a step back here. 10 over radical 3. 200 over 3. Okay, we're all good now. So let's plug it in. 2 times x times y. And let's just do that. 2 times 10 times 200 is 4,000 over 3 radical 3. My units are just units. They don't give us any inches or whatever. Units squared. Units. Units. Oh, this should be a... No, I did everything right. Okay, good. Some of you may be looking at that going, but there's a radical in the denominator. Yeah, okay. That's fine. If you are really, really, really like thirsty to have that radical in the numerator, multiply top and the bottom by radical 3. 4,000 radical 3 over 9. But remember, we've been talking about on the AP test, you don't have to have a simplified answer. And also, I will tell you, once you get to college, literally no one cares about rationalizing the denominator anymore. It's an exercise for children. We are all no longer children, so we can leave our radicals where we like. So this one requires less work, but if you want to give me this one, you can give me this one too. I won't say no. All right. Next one. So here now we have a problem that gets thrown around in algebra a little bit, but here we're going to be a little bit more something here with this. So you're planning to make an open rectangular box. So basically what we're going to do, and this is a very common description, open rectangular box or open cube box or what have you. You're going to take a whatever kind of shape here. Usually it'll be some kind of rectangle. That is going to be incredibly bad to contrast. So let's try this again. There we go. And basically what we're going to do is we're going to chop off the corners. Chop off square corners. Hopefully the same square from each. Again, you know, your art may vary, but the idea is that you cut off the exact same corners on all the sides. So we know that they tell us that this is a 17 by 33 piece of cardboard. So this is 17. This whole thing here is 33. And then what we're going to do is we're going to fold it up to make our box. We're going to make a crease here and here and here and here. We're going to fold up all the pieces to make a box. All right, and then you can have some dimension, and then just the top of the box is open, so we don't have to worry about the top of the box at all. And so what we need to know is we need to know the dimensions of this box, because they're going to be asking for like volume and surface area and stuff like that. So first things first, these are all square corners, so we don't know what they are, so we're going to call all of them X, right? And then you're going to need this quantity and you're going to need this quantity. Well, we know that the whole thing is 17 and we're subtracting 2 x's, so this is 17 minus 2x. And then this is going to be, well, the whole thing is 33. Now we're again subtracting 2 x's. So if you look, our box is x by 17 minus 2x by 33 minus 2x. And your mileage may vary here with the chain rule and the product rule and all that, but I don't know. We want to find the volume, length times width times height, right? And actually, everything's all already in terms of x, so we don't have to do very much else except take the derivative. And I don't know how you feel, it may help to at least distribute this one. It will kind of pay dividends to FOIL this out. I'm not saying that you have to do it, but like 17 times 33. Some of you may be like, just do the multiplication rule. Who cares? It'll take less effort. It's up to you. So we got 561x minus 34x squared minus 66x squared plus 4x cubed. And you can combine these. That's 100, right? I'll put it in standard form because I know somewhere out there someone's going to be yelling at me about that. But it doesn't matter. As long as you combine your like terms to make your life simple. This is our thing we're going to take the derivative of. Again, you could have taken the derivative up here and done product rule for 45 minutes, but I don't know. I think this is slightly easier. So I'm going to move this up a little bit so that we have some room. Maybe I won't. I just want to get rid of you. Oh no, but you're going to make me take the whole thing. Oh, it doesn't even. Okay, so this is what we have here. You know what I'm going to do? I'm going to move this to a new page. I'm just going to take you. You going to let me just take you? Yeah. And we'll come back. I'm just going to insert a blank page here afterwards. This is our function. Let's move you to the top. This is our volume function that we're going to be optimizing. And they said, they want the largest volume. So we're going to go through, we're going to figure out what's what. We're going to take the derivative, 12x squared minus 200x plus 561. And they had to do it that way, didn't they? 561, is that really right? 13 times 17, 33 times 17. Okay. So, like, they don't have anything in common. 212 and 561. So we're going to use the quadratic formula, I guess, to find our x values. Negative b plus or minus the square root of b squared minus 4ac12, 29, all over 2a. Even for all of this being what it is, what is inevitably going to happen is that one of these answers is going to make our problem impossible. What do I mean? So I go through and I'm going to pull out our friendly calculator. Ooh, by the way, we have calculators that are purported to be coming in, which is going to be nice. We'll actually have a classroom set for us. So we can actually throw this in the calculator, 200 plus that ugliness and then 200 minus that ugliness. So we got 200 plus the square root of, I'm going to simplify this to 13072. Put that in parentheses. Insert. Divided by 24. Divided by 24. That gives us one answer of 13. And then the other one we're going to do with the minus sign. This one is going to be 3 point. So why am I not worried about there being two different answers? Well, don't you have to then go and check and stuff? No, you don't. And here's why. Look at what our dimensions are. X, 17 minus 2x, and 33 minus 2x. Hopefully some of you are already going, oh, it can't possibly be this top one, right? Because if I'm trying to have one of these dimensions be 17 minus 2x and x is already 13, this is going to be negative. G. Negative, right? So this first answer, this plus answer, nobody cares. So the only thing we do care about is this answer right here, this 3.563.9464691. And I'll tell you in advance, this is good. If they're giving you something like this is a calculated portion situation. So what are the dimensions of the box? Well, there's 3.5694, right? There's 17 minus 2 times this, right? 17 minus 2 times that, which gives us 9.86107. And then the other one was 33 minus 2x. And this is what the calculator is for. I'm going to be very honest with you. Nope. Nope. 33, I'm just going to click minus 2 times x. We get this. And then now all we have to do is length times width times height. So we got length times width times height. Phew. And then there's our volume. All right. Okay. Sorry for making that out to be more hard than it really is. Again, it's literally just take the derivative, solve for x. Only one of these x's is going to work. Plug that in for length, width, and height, and then multiply them to get your volume. Okay. Easier, back to perimeter and stuff. A rectangular plot of farmland will be bounded on one side by a river and on the other 3 sides by a single strand electric fence. What does that even mean? Well, here's a river, and then the farmland is going to be, you're going to make a electric fence here, and it's going to be a rectangle. And since it's a rectangle, once again, we can call one side X and the other side Y. But we know that the perimeter of this piece here, these 3, is 1400. So X plus Y is 1400. We want to know what's the largest area. So what we know is that the area, which is X times Y, well, we got to get rid of that Y. So let's solve for Y. Let's put that in. And again, I'm going to distribute to make my life easier. Bring it down. Find the derivative, set it equal to 0. Solve for X. So if x equals 350, I need to figure out what y is. Well, 2 times 350 plus what is 1400? Well, this is 700, so y had better also be 700, right? So there's my x, there's my y. With 1400 meters of wire at your disposal, what is the largest area you can enclose? Well, I found the dimensions of the area. Now let's find what the area actually is. X times y. Whatever that is, 350 times 700. Um, that much. 200, 245,000 meters of area squared, right? All right. We're almost done. Rectangular tank with a square base. So here, I want to point out some tricky things that they are telling us. They're saying minimum weight. They don't tell us anything about weight. What do we do? Well, if they say minimum weight, they're just talking about the materials, right? So we don't want volume because these are empty boxes. So what we're going to end up doing is we're going to use surface area. Surface area only deals with the actual materials, so that's what they're talking about in this case. So 32, we've got this is the volume. And it's a square base rectangle. So, again, we're going to draw a figure here. The base is a square. So like these four sides are the same. So why don't we call them all x? And then this height we'll call y. So the volume is going to be length times width times height, x times y. This is our volume. And we were going to minimize surface area. So basically all you're going to do is you're going to, okay, there's one that's x times x, and then the other four are x times y, right? So now we got to get rid of that y. We got to solve for y here. We're going to divide that x squared over. We're going to plug that in. So our actual surface area in terms of x, 4xy, which is 32 over x squared. And we're going to simplify this, make it easier to work with. X squared plus 32 times 4 is 128. X over x squared, we're just left with an x in the bottom. Now we're going to take the derivative and set it equal to 0. And then 128 over x, the derivative of that is negative 128 over x squared. We want that to be 0. We're going to bring that over. We're going to cross multiply. And then we're going to divide, and we're going to take the cube root, right? X cubed equals 64. Take the cube root of both sides. What number times itself 2 extra times is 64? That's the number 4. So there's x. Now we can go back and find y, yeah? So 32 equals x squared times y. 32 equals 16 times y. So y is 2. There's our x, there's our y. The dimensions, length, width, and height, well, x, and y, right? So 4, 4, and 2. Those are our 3 dimensions. Okay. Last one, and then I'm going to give you the rest of the time to work. 2 sides of a triangle are 12 and 10. Find the size of the angle in radians formed by the sides that will maximize the area of the triangle. Okay, so area of the triangle. This one, you got to remember back to geometry. Those of you who had me, I did teach you this. So the area, one way to think about area is if you've got any kind of triangle and you know the 2 sides and you know the angle in the middle, 1/2 times a times b times the sine of theta. So we know a and b, 12 and 10. We're trying to find the angle. So let's do this. 12 times 10 divided by 2 is 120 divided by 2 is 60. They want us to, now we're going to maximize it, right? We're going to take the derivative, set it equal to 0. Derivative of sine is cosine, so 60 cosine. Just divide the 60 away. So we want to know, where is cosine equal to 0? Get out that unit circle. Cosine is equal to 0 at pi over 2 and 3 pi over 2. Now, if you ask me, the biggest angle that you could possibly even consider having for a triangle is just less than 180, right? So our domain for our answer anyway is just here. So if that's 3 pi over 2, nobody cares. The theta that maximizes our area is pi over 2. 90 degrees, right? And that's actually why, if you're looking at a triangle, that's where this formula comes from. We know that the biggest area is going to come from when it's pi over 2, and so when you've got a right angle, you can just use the area formula you learned in elementary school.